Hello and welcome to another Introduction to Astronomy lecture. This is lecture 15, Stellar Evolution Part 1. Today we will be exploring stellar nurseries in the Orion Nebula, which is nearby, and then we will also talk about circumstellar disks and exoplanet detection. That is, how can we tell that there are other worlds being formed around these stars that are forming? Then we'll also talk about protostars and how they form and evolve onto the main sequence and officially become stars. Then we talk about when they officially become stars as zero age main sequence and what that means. Then we talk about the different fusion rates that occur in these stars. We will also talk about red giants. That is a later stage in a star's life where the fusion rates are different and they're no longer on the main sequence. And then lastly, we will talk about how stars group themselves, such as in globular, open, or just various types of associations. So, stellar nebula are where stars are born in amongst the clouds of gas and dust. So we've theorized that stars form from nebula collapse, but if we really want to support this theory, we need to look out into space and find examples of what we've been talking about, areas that have a lot of the raw material necessary for stars to be born. The most massive of these nebulas act like reservoirs for that interstellar material that we've been talking about. And since they have an overall cold temperature, about 10 to 20 Kelvin, this is the right conditions for the birthplaces of stars. So when stars are first forming in this overall low temperature and low pressure but high density environment, it really works in gravity's advantage and helps provide the necessary conditions to start nuclear reactions after the nebula starts collapsing. And then when I say collapse, I mean collapsing gravitationally. So now let's talk about Orion and the massive molecular cloud that's in the Orion constellation. So there is a lot of nebula in the that make up the molecular cloud. Most famous of which is the Orion Nebula, which is located down below the belt near the sword in the constellation. And so this whole region, the molecular cloud, contains nearly 200,000 times the mass of the sun in raw interstellar material that's spread across about 100 light years. And so in his sword, in that the Orion Nebula itself, there are nearly 2,200 young stars that are very young, that are less than a million years old, that are glowing extremely brightly in the infrared and heating up the gas and dust around them. And so when we look at the image on the right, we can see the glowing region that is not visible when we look in the optical on the left of the two images there. But in these regions, we find that star formation is actually not very efficient. Only 1% of the raw material available actually turns into stars, and then the rest of it gets blown away and then has to start the whole process of collapsing down into a star again. So, while any like the specific catalyst that starts star formation is unknown, there's good evidence that the first generations of stars triggered the formation of more stars sequentially. And so this process is known as triggered star formation, when one forms and blows away on the gas and dust around it, that's then going to cause other areas to then experience the right conditions because new material will have been blown in. When a massive star forms, it emits a lot of radiation and has very intense winds, which expand the nearby gases. Once that star's fuel has been exhausted, it then explodes and releases even more energy, heating the gases around it. And so over time, these ultra hot gas piles cool down into cold regions, which then start to slowly coalesce and the material compresses until the density has increased enough. And eventually, if the density is large enough, gravity will then take over and stars will begin to form again out of the material that was left behind by previous generations of stars. When we look with infrared telescopes at these nebula and find young stars that are forming, they are all surrounded by circumstellar disks. These circumstellar disks are uh, able to be seen in the infrared because they are being heated by the young star in the center. So the dust particles in the disk gather gravitationally to form what we call planetesimals through accretion. But the dust itself initially covers a much larger area of space than the exoplanet systems ultimately do. To observe the formation of extrasolar systems, we study that infrared radiation of the dust material itself. And from observing that material, we can conclude that young stars have circumstellar disks that range from anywhere from 10 to up to 1,000 AU. That's pretty large distance. For reference, Neptune is at about 40 AU in our solar system, if you remember. Obviously, the comets go much further out, but some of these other systems may have much uh, wider varieties of planets because they have somewhere between the masses of 1 to 10% of the mass of our sun in the disks themselves. If you remember, in our solar system, our sun makes up 99.8% of the mass of the entire solar system. And so we can conclude that all stars begin their lives with enough material to gravitationally create planetary systems that have the exact that form via the exact mechanisms of our own solar system. Okay, so we can see that young protostars have enough material around them in these circumstellar disks to make planets, but how do we know that those actually form into planets? Have we seen other star systems with already formed planets? And the answer is yes. The first exoplanet was discovered in 1995, and we now know that most stars form with planets, which we refer to as exoplanets. That is, planets that are outside our own solar system. And exoplanets can be found and studied by a variety of methods, but the majority are found via two methods. So the first is they look for a Doppler shift in the host star's radial velocity, and that would be due to the gravitational perturbation of an exoplanet. So if an exoplanet is going around a host star, the pull of that exoplanet's gravity will cause a little bit of the material on the surface of the star to have a different radial velocity. And so you can tell that there is something pulling on the star. And so this has found hundreds of exoplanets, and it's also very useful because it lets you know the mass of the exoplanet because it's from a way that uh, you're looking at the gravitational effects, and so that's intrinsically linked to mass. The other method that's been very useful for finding exoplanets is the transit planet light curve method. So this is when we can actually see a good example on the right in the lower image. So if the orientation is correct from our viewing angle here on Earth, and an exoplanet goes in front of a star, that will cause some of the star's light to be blocked by the exoplanet and cause the brightness to momentarily decrease while the exoplanet goes across the stars from our perspective. And so that is called a transit when the exoplanet is going in front of the star. And so this method has found thousands of exoplanets, and while it doesn't give us a mass estimate, it actually gives us a size estimate, a radius estimate for these exoplanets, because we can estimate their size based on the decrease in the light. And if both detection methods can be used, astronomers can then measure both the size and the mass of the exoplanet. And so while direct methods would be more desirable, it's pretty difficult due to the small reflective qualities, and often this only applies to gaseous and massive exoplanets. So for early stellar evolution, it always proceeds in the same steps. So we have this image that shows us some of the steps. And so we have The density of our nebula that's spinning slowly increasing, and then gravity begins to overwhelm the outward pressure of the material. And then the protostar forms in the core. This is a gravitationally contracting precursor to the star. It's not a star yet, it's a protostar. And so from the conservation of angular momentum, because this protostar is spinning, this begins to collect material along the poles while the disk of remaining material forms along the equator. This results in an emitted stellar wind confined along the poles. Over time, once the protostar's final mass has been reached, the remaining material along the poles is swept away by the stellar wind, and the stable star is left behind and is surrounded by a forming circumstellar disk. That's when the planets begin to form. And for masses less than or near the mass of our sun, these newly formed stars are called T Tauri stars, named for the brightest member of the Taurus constellation, which is one type of this star. And while the most massive stars actually skip this stage during their formation. So now let's talk about how protostars evolve onto the main sequence. So at first, protostars only exhibit gravitational contraction to remain stable, but they are on their way to the main sequence. They are initially pretty cool, only about 1,000 degrees Kelvin, and have a very large radius and low density. So we can see this image on our right. This is an example of different evolutionary tracks that protostars take on their way to the main sequence. On the x-axis, we have our temperature in Kelvin, and on our y-axis, we have our luminosity in terms of solar luminosity. So we can see that these different protostars of different masses have slightly different evolutionary tracks on their way to the main sequence. As they contract, the heat builds, and so the pressure remains constant outside until the outer layers swiftly fall down, and this rapidly increases the density and decreases the luminosity of the young protostar, which traps in heat. And this is where we see the vertical lines, the vertical black lines on this diagram right here, is during this contracting and then outer layers falling down stage. After this contraction and after the collapse, this slows down until we reach some hydrostatic equilibrium. That is, the pressure, the internal and external pressures and forces are equal, and this gives us a relatively constant luminosity. As the trapped heat radiates from the core, the star slowly moves to the left on the HR diagram as the surface temperature increases. And this is where we have these horizontal black lines on the HR diagram from these evolutionary tracks. And this continues until the star reaches the necessary internal temperatures for hydrogen fusion, and then it officially becomes a main sequence star at what we call zero age. On this, that's where this is that solid red line. And so we refer to zero age as the moment that a protostar reaches the condition for hydrogen fusion in its core. But that zero age point on the HR diagram depends on the mass of the star. So we can see that these different protostar masses all reach that red line at different temperatures and luminosities. So less massive stars become stable and reach zero age main sequence at much lower temperatures and luminosities, whereas much more massive stars have a very different point at which they reach zero age main sequence. A young star begins its life as a zero age main sequence star once it begins that hydrogen fusion into helium in its core. This is what we call then a prolonged adolescence because it spends 90% of its life doing exactly that, fusing hydrogen into helium in its core on the main sequence. And so we say that it's zero age because it hasn't fused any hydrogen yet into helium. It's just reached those conditions. But then as it spends its time on the main sequence, it then ages as it uses up some percentage of its available hydrogen. But surprisingly, only 0.7% of hydrogen's mass is converted into energy during the main sequence, and the total mass of the star remains relatively unchanged. So these stars on the main sequence are incredibly stable. They aren't blowing away very much of their mass in their solar winds compared to the later stages of their life. And during this main sequence period, stars slowly move along the HR diagram, increasing luminosity until they have exhausted the hydrogen in their core. So how long do these stars last on the main sequence? The number of years that they last on the main sequence depends on the mass, but it's not actually as simple as more mass means more lifetime, because actually more mass means more fusion. And to be even more clear, the lifetime of a star in the main sequence depends exactly on how much nuclear fuel is available and how quickly will it be exhausted by fusion. So actually, more mass means a shorter lifetime. High mass stars exhaust their fuel way more quickly because they have a much higher temperature in their core. And this results in higher luminosities as well while they're on the main sequence. So a star like our sun that has one solar mass will last nearly 10 billion years on the main sequence, while stars that are about 40% the mass of our sun will last nearly 200 billion years on the main sequence. But then stars that are 40 times the mass of our sun only have lifetimes of about a million years. And this explains why that triggering star formation that we talked about is actually possible, because if massive stars have shorter lives, when they die, their death will trigger the birth of many more stars around them in that uh, very ample interstellar material. And so when we talk about astrobiology, it's really important to keep those relations in mind for the lifetimes of stars, because we know that life on Earth evolved in the span of about 4.5 billion years. And our sun's lifespan is about 10 billion years. So we are somewhere in about halfway of our sun's lifespan. So for more massive stars, that means that they probably don't live, the stars don't live long enough to support the evolution of complex life. A star that is 40 times the mass of our sun only lasts a million years, so any planets around those stars are not going to have much time to develop anything complex in their chemistry in terms of life, very likely. But we don't know that for sure. This is just our theory. So now we're going to talk about the next stage of stars in their evolution, the red giant stage. So eventually, all of the hydrogen fuel in the core is going to be converted into helium, and this is what we call hydrogen core exhaustion. The fusion of helium requires much higher temperatures, about 200 million degrees Kelvin. So gravity takes over once there is not a lot of that outward pressure from the fusion of hydrogen, and so the star contracts gravitationally. However, this gravitational contraction then causes that infalling material to be converted into heat. And so this heats up our core again after it has contracted enough. But during this contraction, the outer layers of the star are then heated up to 15 million degrees Kelvin, which in the outer layers, there is still hydrogen because it wasn't in the core. And so then we have some fusion that occurs out in the outer layers. Energy from hydrogen fusion in these layers and helium contraction surrounding the core perpetually heats the outermost layers of the star, which causes it to expand to enormous proportions. This is what we call that red giant. This heat infusion also increases luminosity, but the expansion of the star's outer layer causes the surface temperature on the star to decrease, making it simultaneously larger and cooler, but more luminous. And so this is the red giant. But when you are more massive than if the sun and really a supermassive star, you can become a super red giant. So now we're going to talk about how we can use star clusters to study stellar evolution. Since these phases of stellar evolution can last millions to billions of years, which is far longer than we've had to observe as astronomers, we need to look at groups of stars to study stellar evolution. So we can use these clusters that are relatively close together in space and are being held together by the gravity of all of the stars in that close space. They are moving with one common center. And so assuming that, that means these star clusters formed at nearly the same time and from that same nebula, and they only differ in what phase of stellar evolution they are currently in. So the three types of basic types of star clusters are globular clusters, open clusters, and stellar associations. So the first, globular clusters, are the oldest and rarest. They are often very round, hence that globular name, and they can be found near the center of galaxies with diameters somewhere between 50 and 450 light years. They often contain hundreds of thousands of very old stars. They are close in distance to each other, but still very far from our sun. An example of which is Omega Centauri, with the brightest of its several million stars being red giants. Then we have open clusters. These are some of the smallest groups. These can be less than 30 light years. There are a lot of them, and they are found in galactic disks. They also contain far fewer stars. Open clusters can have anywhere from maybe 6 to 30, 40 stars, but nowhere close to a globular cluster, which, as we said, had hundreds of thousands of stars. So these open clusters have ages that range from of stars from being 100 million to a few billion years old. And all the stars in open clusters are spread and have finite lifetimes before the stars escape the gravity of that common center. Lastly, we have stellar associations. Associations are groups of extremely young stars with about 5 to 50 bright O or B type stars scattered over about 100 to 500 light years in diameter. And these groups have very short lifetimes and are often surrounded by many smaller, less luminous stars. So we can actually use the HR diagram to do a lot of things with clusters. So when you plot all of the stars in a cluster on the HR diagram, you get a nice spread that tells us several things. So you can infer based on the number of stars in the different stages how old that cluster is. So young clusters that are a few million years old have massive stars that have exhausted their hydrogen fuel, and the less massive stars are still approaching the main sequence. Star clusters such as NGC 2264 and those in the Orion Nebula match these descriptions because they're still containing lots of their original raw material. As billions of years pass, the stars in these clusters will progressively make their way up the HR diagram and become the most massive will become giant stars. Older clusters that are a few billion years old contain fewer stars in the main sequence and ultimately have no stars near the top left where the more massive stars live. And this leaves only that population of the bottom low mass stars in the cluster still when you plot them on the HR diagram. The older the cluster, the lower the region of the main sequence where these low mass stars turn off towards the giant stage. And this is a point known as main sequence turnoff. These oldest globular clusters show that the lowest luminosity, lowest temperature stars in the main sequence are present. Globular clusters are the oldest structures in our galaxy, and the youngest of which are still older than the oldest open clusters. This gives astronomers some of the best estimates on the age of our galaxy. This concludes Lecture 15.